I'll get to the notebook in a second, but just a little bit as motivation. So I'm the PI on the Greenland Ice Mapping Project, or GRIMP. It used to be called GIMP, but we gave it a little bit more name appropriate for the times. And we produce both SAR image mosaics of Greenland and velocity maps. In this tutorial, I'll talk about the image maps, and then in the following tutorial, I'll talk a little bit about the velocity maps. And this is all possible because a lot of the work is possible from a lot of help from Scott. In particular, he really got me focusing on converting all our data sets to cloud optimized geotiffs. And for the tutorial, we're going to focus on what you can do in the notebooks, but I just wanted to show that there's a lot you can also do with cloud optimized geotiffs otherwise. So we're getting to the point where we're producing huge volumes of data. The image data set now, I think it's something like 2 terabytes, which is way more than you might want to get on a laptop, especially at the rates that Apple charges for storage on their laptops. So often it's more convenient to leave the data on the server at NSIDC. What you're looking at here is a 25-meter mosaic of Greenland that Sentinel collects. It was collecting every 6 days. One of the satellites died, so we've gotten to 12 days now. I've only got 4 images queued up here. I didn't have time. I have got a project with more than 300 images in it, but there's an environment variable I have to set somewhere on this Mac, which I haven't done before. If it has too many open files, it dies. But you can basically, just real quick by way of demonstration, this is pulling it off the NSIDC server. So you can basically browse the whole data set. Where did it go? You can browse the whole data set almost as though it were on your disk from QGIS, all 300 images. It'll, of course, run into problems if you try to render 50 images at once, but as long as you're careful and only turn one image on and off at a time, it works really well. And that's all through the power of, let's see, does this preserve things when do you see the Jupyter Notebook now?
Yeah, we do. If you could make the font a bit bigger, that'd be great.
Oh yeah, I have to put it in presentation mode. Thanks for that reminder.
Yeah, great.
So I just wanted to show that, yeah, you can access the data different ways. Here we're going to basically take advantage of 2 packages I've written. It's basically going to review, or it includes many of the concepts Tasha and others have shown. It's going to use X-arrays. It's going to use DASC. It's going to use stacks of or make building stacks within X-arrays. There's a little bit of pandas in there. And rather than, I use these data a lot, or these functions a lot, and rather than copying and pasting text between Jupyter notebooks, which can be frustrating, especially on the 5th or 6th iteration, you decide you can improve something, and then you've got 5 earlier iterations that aren't improved. So I like to put it all in a nice package that I can modify and then have use everywhere. It makes things much easier. Unfortunately, it's not always maybe the clearest for tutorials, but the links to the code are all in the notebook here, and they're all on the web, on GitHub. So first, I'm gonna just do the setup stuff here. Now, basically for the both for the QGIS and this notebook, we make use of GDAL's, I don't know if it's pronounced VSI curl or VisiCurl, but it's a virtual file system that takes care of a lot of the authentication stuff you need to do when accessing files. And I've got a login here. If I run it right now, it'll just tell me I'm logged in, but that's because there's a Netrc file that has my username and password in my home directory. And if I start from scratch, so I'm going to remove that file. While I'm doing that, so there's this step will basically make these files, these cookie jar files, and that's something that GDAL needs to tell it how to connect the username and password with the website. I don't actually think it uses the cookie, it just somehow gets the website information from there. And if I enter the credentials, it logs me in. In doing so, it made a Netrc file. And if that makes you uncomfortable and you're running the thing, just remove it at the end. It should be pretty safe, as long as your Earth data password is not, used for your bank account and things. And the file is readable and writable only by you. So now, this makes it a lot easier when you're running the notebook multiple times to sort of have it automatically log you in. So we're going to look at an area in northern Greenland, Zachary Istrom. It's next to 79 North, and it's basically one of the outlets of the Northeast Greenland ice stream. So I've just conveniently saved the coordinates of the area we're looking here in this dictionary, this B-box, bounding box dictionary. And then I've also just got the X and Y coordinates saved as a rectangle here for plotting later. And I should mention we're doing everything in polar stereographic for the Arctic, 3413. I can't believe I'm blanking on it. So the first thing we want to do is search the archive for data. And we have a tool that does basically a CMR, common metadata repository, searches the NASA archive. We're going to be working with images. And those images can come in different flavors. They're either an image product, a Sigma 0, and or Gamma 0, Sigma naught or Gamma naught products, which I can talk about a little bit more below. So for the search, we basically want to be able to specify a search range. We want to specify a product filter, which in this case would be image. And then we can put those in. We set up our URL object, and then we do the first search. So it's basically done the search for us at this point. If we weren't happy with the search results, we could change those parameters and do a different time range. Here I've picked 10 images. I could have, again, got the Sigma naught products if I'd wanted. That should change them up. Not sure why. Oh, there they are. Okay. So now I'm going to go, it's easier to rerun the whole step. We're going to be using the Sigma naught and Gamma naught products below, but again, since we don't actually, we know what we want right now, I've just put semicolons here to suppress the output. So it's just basically searching for those data. Now we're going to use this NISAR image series object, and we'll see kind of a parallel object for velocity. They're all derived from the same base class. And this object will basically build an X-array like we saw yesterday, more or less what Tasha showed you, using X-array and Rio X-array. And it stores it in an X-array. At this point, it's called subset. In this case, subset will be all of Greenland. So, and here's this nice image map. You can see at 25 meters, it's actually a pretty big image, roughly 60,000 by 100,000, and it's 10 layers deep, 10 time layers deep, and it only, in this case, only has one band. That's 60 gigabytes, which isn't a tremendous amount of data, but you might not want to download all of that, and it certainly would take a while to do that. And we're only interested in Zachary, so why would we bother to do that? So we can basically put our bounding box into this subset method, subset image method of the image series, which is basically doing a Rio X-array. I think it's a clip box, and a little bit of other bookkeeping. And there you can see now, with the cogs, we can see the different tiles. We can see we've got something down to a much more manageable size. It's only about 80 megabytes. And it's all stored on NSIDC still. It's basically done a lazy open at this point. With Dask, as we heard yesterday, it kind of queues everything up and will do it at the moment you really need it, like if we were going to generate a plot. When you're working with big stacks, sometimes it's better to actually load the data directly, because there's only so big a cache, and sometimes if you open too many images at once, it will have to re-download the data, and that can be time consuming. So this load remote, this actually went really quickly because the data were cached. I think it would have taken about 15 seconds. The original took about 15 seconds when I loaded it this morning. So now it's got all of that data stored in memory. And I can run these other two, the gamma series and the sigma-naught series. So another advantage of COGS is they have image pyramids in there, or overview images. And that's nice. For example, if we just want to see where we are, we don't want to download a 60,000 by 100,000 thing. It would choke ImShow if when you tried to render it anyway. So we just told it overview level 4, which gets the resolution down to, sorry, I'm just manipulating the screen. It's 32 times 0.25, so what, 800 meters? No, it's more than that. 8 kilometers. Anyway, I'm not doing math on the fly here. So the 3 types of images mentioned above are image, which is basically a byte image where we just use the color stretch of the data that enhance features. And this is really nice if you're trying to digitize glacier terminus front or see features, but it's just byte data with an arbitrary nonlinear scaling to them. The sigma 0 and gamma, or sigma naught and gamma naught, are calibrated radar cross sections, and those kind of cross sections you would use maybe if you were doing a study of looking how the fern is changing during melt, and you really want quantitative data. Sigma naught is, that's not, well, I should back up a second. When you image with a radar, you get a lot of terrain distortion if the it's measuring the range to the target in the cross-track direction. So if you're ranging like that and you see the face of a mountain, a big part of the slope is being imaged all in the same range bin, where if you're on the back side of the mountain, a couple meters of range will be chunked up. So the image gets really shortened up in the front side and really stretched out in the back side. We've corrected or put everything in the right place when we've mosaicked this data, even in the byte scale data, but we haven't necessarily corrected the fact that it's brighter on the mountain side that's facing, because it's seeing much more of the mountain in one range bin. So it'll be much brighter, and then it'll be much darker on the backside. So there's geometric terrain distortion, which is again putting the stuff in the right or the wrong, or the data get put in the wrong place. And then there's radiometric terrain distortion, which has to do with things that are brighter or darker than they should be based on their surface slope. So with the sigma naught product, that terrain distort, everything's put in the right place and it's normalized, but it's not, hasn't taken into account the topography, whereas the gamma naught products actually attempt to take this DEM, use the surface slope, and actually remove the effect of the topography, or the brightness variation that's direct result of the topography. So here we demonstrate on Zachary all 3 images, and you can see here we've used that overview image, makes for a nice little inset, and you can see this red box is the region we're looking at. So here we just have bytes, or the digital numbers. We've basically used the series that we built above. We've loaded it, and now we're just using the method display image for date. So we picked one of those images out, and this percentile here, you can get some very extreme rare values in the image, which will cause not a very good contrast in the image. So we just put in this percentile, and that clips everything from 1 to 99th percentile. I've turned the axis off, and basically, yeah, just displayed each of these images and then made an inset axis and done the same process for up here. There's not a lot of topography effect in this image, but if you look kind of in these lower regions on the 2 images on the left, you can see there's some texture here that's basically the topography. And if you look on the gamma naught here and on this island here, you see that it's much flatter looking, and that's more or less what the backscatter would be if we could just take the rock, in this case on these islands, and just flatten it, and it should all be roughly the same cross section. This is 25-meter data, and at the way it's rendered at this size on the screen, you can't really see the full how much we can actually see that resolution. So here's a figure just that basically progressively zooms in on that image. So this is the original image, and then we're going to look at this white box, which is here on the right, and then the inner box down here in the lower left, and then the lower right. We zoomed in pretty much all the way, and you can see detail. You can see individual icebergs here. You can see lakes over here. There's all sorts of features visible in the image. This is actually the calving front here. Here's a little bit more radar distortion. Even if we had the DM, we can't really take out. This is a shadow, so the radar is looking from the lower left corner, more or less, and I can't see the front of the glacier, so you get a radar shadow there. So once we have these in the image series object, there's various things we can do, just more or less using some of the X-array functions, the ability to run things on the whole stack. So we can compute the mean, we can compute an anomaly. So basically it computes the mean, and then for each image in the stack, it subtracts the mean. And then we can also compute the standard deviation. So if we run all these, here's the mean image now, which is going to look a little blurry because we're looking at ice that's moving. So the image has moved over time. We can look at the standard deviation here. We see in the front of the glacier where the melange is moving around, we see there's a lot of variation. The image is not static, unlike up in the lower left here where it's just ice sheet. And we can see some more standard deviation on the lakes. And that's probably the lake ice growing over the winter and getting deeper and changing the backscatter. And you can look at an anomaly map here just for one particular date. And you can see lots of variation here. And in this area here, you're seeing crevasses moving relative to the mean. So that makes it images like this useful for example, I think Tyler's going to show how you can set the window length on to get better resolution. So you might want more resolution here where you've got crevasses changing, and less resolution here where everything's pretty smooth. Another thing that if you've got data, often you want to do is interpolate. So basically we have an interpolation function, which is right here. And we can specify whether we want to interpolate, specify our input coordinates in units of meters or kilometers. Everything's done internally in meters, but often for plots, I prefer kilometers. So I often turn the kilometers on. And you can get the interpolation here as just the standard NumPy array, or you can use this return XR and it'll return the result as an X array, whatever your preference. So we can just plot the time series, and not a lot going on here. I'm not quite sure why it was so bright at the beginning and then started to darken up a little bit here. But we're looking at the sigma naught, sigma naught, gamma naught, and sigma naught at this red star here. So on some areas of the ice sheet where you've got good seasonal melt signals, it's interesting to run the full 5-year time series, and you can see some of the seasonality. If we actually run the full series, it might have taken, depending on your network, but like 3 or 4 or 5 minutes to download. But once you've downloaded the data and loaded it in one of these series, I think I don't demonstrate it here, but I'll do it in the next section, next tutorial. It's very easy to just dump the data all to a NetCDF, which is relatively small in size, and you can analyze it later. Another thing we provide from the Greenland Ice Mapping Project is the terminus positions of all the major glaciers in Greenland. Nominally every year, though, there's some gaps where we didn't have radar data. Again, we use our little search tool. That gives us a set of URLs. And again, because we have this login stuff going on, this is all behind the NSIC Earth Data firewall. Because we've set all that up, we can actually just do the GPD Geopandas read file by appending this VSI curl to the actual URL. And that just reads it in just like a regular file. And once we have that, we can just make a plot, and you can see all the fairly dramatic changes that have occurred in on Zachary since 2000, which is this blue curve here. There was a much more extensive shelf, and progressively over the last couple of decades, it's broken up and retreated, and it's been slowly retreating, but it's a bit more stable here as it's probably gotten more of a grounded calving front here. It's not so much shelf that can rapidly retreat. This is an interesting feature in the top upper right here. This is basically a remnant bit of ice shelf that's just stuck up there, but it's not being fed by anything. And it'll be interesting to see how long this thing stays here. The original glacier was fairly protected by sea ice, and much of the retreat may have happened as some of that sea ice went away some summers. But there are actually some of these icebergs, when they calve off, they can actually stay locked in that matrix of sea ice for many years. So to summarize before Tyler takes over, we've basically shown how you can work with a 2 terabyte data set remotely on your laptop, and either through a notebook or through other programs as well, like QGIS. We looked at a fairly short example, but it's not any harder other than, maybe you need to go get a coffee while you're waiting for the data to download, but you don't have to download the full 2 terabytes, which would mean you kind of start it downloading and then go get a good night's sleep and come back. We have several other notebooks that demonstrate different aspects of working with the GRIMP data, and you can just follow the link there if you're interested. And with that, I just need to, oh, here it is. I'm going to surrender the screen to Tyler.
All right, are we on a new screen?
We are.
All right. So Ian just went over how to use this huge image archive. And here we're going to go and see a way of going through all of the ATL03 archive, which is also quite big, using a tool called SlideRule. SlideRule is an on-demand service that is a collaboration between the University of Washington and Goddard Space Flight Center. It enables on-the-fly subsetting of ATL03, and also the generation of a land ice-like product. So taking the geolocated photons and fitting segments to them to get a surface fit. It accesses all the data that's available on AWS through NSIDC, reading the HDF5s through a program called H5 Coreo, which is a cloud-optimized read-only program that was developed by JP Swinski as part of this project. It is a really cool tool for both data exploration and also for science applications. It's really fast, which is why I often use it for data exploration. And its basic thing is that it creates something like ATL06. But as opposed to using 40-meter segments that are overlapping by 20 meters, you can adjust those parameters to fit your needs as a scientist. And so if you are, say, looking at a heavily crevassed area, you can use a shorter segment length that might be better suited to fitting to those sorts of surfaces. You have control here. We start out by initiating the SlideRule API by calling the URL that would be used for accessing. This builds a table of AWS servers available for us to process data. We then can select features that we would want. This is just a smaller subset of the features that are in SlideRule. We have more photon classification schemes. We can use the ATL03 photon confidence levels. That is a number between 0 and 4 on if we think it's background or if we have very high confidence that this is signal. We can also use the ATL08 land classification, whether we think it's ground, canopy, top of canopy, which helps in some applications really being able to snap to a surface where we have vegetation or snow or some other geophysical thing that might interfere with getting surface return. We also have an experimental photon classifier that I'm not showing here called YAPC, but we talked about a little bit in the breakout session yesterday. All the mapping, well, a lot of the mapping that I use is similar to what Philip was showing through leaflet maps, which are interactive maps, which we can build here. A lot of our early testing was at Grand Mesa, so that's the default. But I like to look at Rainier, which is our big resident volcano. And then we can add certain layers. So let's say we wanted to have the Randolph Glacier inventory and some imagery. So we can add that to our map. I just realized that I should have put that in the bottom slide or bottom cell. Anyways, going on the fly here. So here's Rainier again with an image and the Randolph Glacier inventory. We can then draw a box around that or a polygon, whatever we want. Close. And then we submit that to SlideRule. And we don't have enough time to get a coffee. Typically, this takes anywhere from 10 seconds to a minute. So I don't have coffee close enough to me to get it. And then what this is doing is that it's taking our parameters that we set, submitting it to SlideRule, and then getting our elevations. We can inspect what they look like. This comes back as a Geopandas GeoData frame. And this has a lot of the things that we would see in ATL06. So we have our estimated height. We have the along track distance, the delta time, which is GPS seconds from 2018. And we have our surface slopes. With SlideRule, we have it so we can add it to the map as a GeoData object, which then will plot our data on the map. Not quite as quickly as SlideRule does, because here we're no longer in our nice SlideRule instances, we're doing it locally. But then we can look at things. So we can inspect what they look like by hovering over them. We also, since we were talking about Greenland, have polar stereo maps, and we can add in Arctic dim, go up to Zachariah, Istrom, find a bit with crevasses. So looking at Arctic dim, we can see some crevasses here. Do our little box there. Do the same sort of submission. Now, when we're in more polar regions, it can take a little bit longer, just as the number of ATL03 granules that it has to look at is a lot larger as we go further and further towards pole, which is good in some cases because, yay, more data. But here, these can take about a minute. And if you go really close to the pole, you may start running into our built-in training wheels stop, which is that we limit the number of granules that someone can run to 300 granules. So if you use a big polygon or a small polygon close to the pole, you might run into our training wheels. And I could talk about how to go into the more advanced mode, but we do that just so that you don't make a huge request that you don't need right away. All right, so that's done. And we can add this data to the map. Here. And so we try to make it be as simple as possible for you to use ATL03 and also create segment fits using ATL03 data that are more customized for what you may need. In the unreleased version of SlideRule, you can also click on these particular RGTs, and you would be able to create a plot of the track by just clicking on it, and you can do some inspections. But we're using the version of SlideRule that is before I started tinkering with it over the past week in preparation of this. So I know that 528 was good, I think. It wasn't that RGT. Let's say this one. And all this information, you wouldn't have to do this sort of investigation. So, all right, this is what the track looks like. We can see that there's some wobbles, which could be crevasses, but at a 40-meter segment fit, it might be something else. They could be more like dunes. So it's like, all right, let's go back and let's use a smaller sort of segment length. So let's now go to 20 if I can drag it. Maybe I can't. Internet. All right, we're good. 10. We'll up our iterations, and then we'll lower the spread. What this spread is that it's the minimum length of photons within a segment for it to count as valid. Typically, I do half of whatever I want the segment length to be. This is basically so that if you had a 40-meter segment, but you only had 5 meters of photons in it, that probably is not going to give you a great segment fit. So we give it the ability to adjust what you would want. The number of iterations is the number of times it will try to fit to a surface. We also have the minimum number of photons for it to be valid. And these are more error type on how big of a spread of photons that we can have for a segment to be valid. All right, so we're going to redo now with our shorter segments. So we're going to have even more data than we did before, as we're creating basically 2 times as many segments. But again, this is all on the fly, and we're doing this with working from home. Sorry about that. All right. You don't need a Earth data login to use SlideRule. You just need the software. We are providing this as part of a budget paid for from the ICESat-2 Project Science Office. And so you can use SlideRule in a Jupyter notebook. We also have a online voila test where you can explore using SlideRule for your purposes and review it with a ATL03 photon fit. It's working a little bit slower than I would have said, but. So these cycle plots are also now in SlideRule for the new version, so you don't have to code that up yourself. We have some built-in plotting that I've put in over this past week. So you could create plots like this of seeing how the surface changes for every cycle. You can inspect a single RGT for a single cycle. and we're adding more and more capability for visualization as things go on. We have some saving capabilities as HDF5 and NetCDF so that you can save your outputs. And another thing that I added this week is that you can read back the parameters that you wanted. So let's say you had an analysis, you found something that worked great, but now there's new data. You want to rerun it. So you can read from a prior file, get the parameters you used, and then resubmit to SlideRule using those same parameters. And that's something that, like I said, I added yesterday. Are we done? We're done. Woo. So let's make this plot again using these new shorter fits. So now we're starting to get something that looks a lot more like crevasses. So if we zoom in, a little bit more choppy, a little bit more crevassed. This definitely looks more like a crevasse. So by adjusting the fits, you can fit parameters, you can extract surfaces that you would want. Anybody have a region they want to look at? Throwing it open, we can go anywhere.
Hi, Tyler. I had a question rather than a your region. So can you go back to that figure you were just showing with the multiple cycles? So yeah, can you zoom in a little?
To where?
Anywhere, doesn't matter.
Okay.
Yeah, okay, that's good. So those differences in height, I mean, obviously you're looking at a snow surface, so it's going to change in height. But do you think are those real differences in snow height, or is there some variation that's coming from, I don't know, how the data are the height is being calculated?
So these would be differences in height, whether it's, we're also quite close to the ice front, and so we could have some dynamic effects going on here. Let's see, yeah, we're looking at this 599 to, so 7 meters. That's not, I mean, it's not a crazy amount of thinning over 2 years. It is a lot. But if we stroll over to Yakupshav and Isbray, I think over the same time period where we'd look more at like 20 meters. And so some of this is going to be snow. Some of it could be dynamic type effects, just being this close to the glacier front. So I would say that this is an actual height change, whether it's the actual drivers would take investigation on what's happening. Yeah, so we could save our file. And then we would be able to reread it. And then you don't have to use the leaflet maps. You can use a predefined region. So we took our bounding box from the SAR imagery at this bit, and we converted it into a GeoData frame in with a coordinate reference system, and we built a polygon object from that. SlideRule has a built-in from GeoData frame reader. So if you have a GeoData frame with polygons or multi-polygons, SlideRule will take that and be able to use it. And then here I'm adding in some time bounds using the exact same start and end timed as the SAR image. And then I made a SlideRule request. I did this while Ian was talking, just for the sake of time. because we're using geodata frames, as we learned yesterday, we can convert them from one coordinate reference system to another with the toCRS function. And we can use our image series from the SAR image series as a base map to use on top. So if we wanted to compare data, this would be one way that we can do it. That's what this sort of plot looks like. So I made a request for SlideRule elevations using a shorter segment length for the bounding box that was provided for this image series, and then I could plot them on top. Now, how this could be used is, instead of interpolating these particular SAR images that we have available from higher up in the notebook, we could say interpolate velocities. So if you were wanting to advect elevations with the velocity and use like a Lagrangian type reference frame, you could use the NICER tools that Ian talked about and SlideRule to get the elevations for a particular time and advect them using current velocities. And thanks, Scott, for adding the note that this plot takes a while. It did. It took about a minute and 30. So here what I did is I interpolated the sigma naught and gamma naught images to our SlideRule returns. And so you could do something similar with velocities and create that. So SlideRule is a great tool. It is pretty simple to use. You can tweak things how you want. You can go wherever there is ATL03 data available, which is pretty much everywhere outside of the pole hole. And you can adjust the fits however you want. So if you want long fits, you can do long fits. If you want short fits, you can do shorter fits. We have some interactive mapping for context, and we're adding more and more all the time. And so SlideRule is great for ICESat-2, but it's also a sort of experimental platform for how data services could be from NASA in the future. So right now we have the standard products of ATL03, ATL06, 7, 8, 10, 11, all the way up to the 20s. But what we could in the future have is these on-demand services of being able to serve these low-level products and being able to run the algorithms that are used to generate the higher level products, being able to tweak them on demand to suit your needs. So here with SlideRule and ICESat-2, we are doing a recreation of most of the ATL06 algorithm. But this could be used in other applications where you have both lower level and higher level products and being able to tweak parameters. And that was sort of the overlying goal, is as a demonstration platform of we can do this quick and fast and make adjustments. And this project has also helped the ICESat-2 Project Science Office on thinking of ways of that they can tweak things in the future. We have this experimental yet another photon classifier as part of SlideRule, so we can see good parameters that could be used for land ice and terrestrial purposes. And so it enables the Product Science Office to test future features without, generating all the products with that. We could use these on-demand services and using cloud access to data provided by NSIDC.